Coming to our example on cracking moment calculation, we have been given a simply supported beam, as you can see in the figure. Its total span is 15 feet with a loading of 2 kg per feet. Its section is also given having width of 15 inches and total depth of 30 inches. This beam is reinforced with 4 No. 8 bars. The concrete strength used is 3000 psi. Our requirements are to calculate the cracking moment and then check if this section cracks under the applied load. So this is our section. As you can see in the figure, we have width of 15 inches, the total depth, which is not given here, but it is 30 inches. Here we have reinforcements in this line, the effective depth, which is the depth of the beam till the centroid of the steel is D, and D is 27.5 inches. Normally, we have a D 2.5 inches less than the total depth of the beam. This is because and this is in the case of single layer of reinforcement bars. You have to provide 1.5 inches minimum concrete cover, which is clear cover, and then till the centroid of the bar we assume number 8 bar, so that is um, zero point 0.5 inches, and we have we assume a stirrup of number 4 stirrup. Its diameter is also 0.5 inches, so total is 1.5 plus 0.5 plus 0.5, 2.5. So we take it to be 2.5 till the centroid of the reinforcements. We'll be discussing it in detail once we go into our other solved examples. But for now you have to just remember that D is 2.5 inches less than the total depth of the beam. We have a strain profile. As you can see, we have compression in the top concrete fiber, tension in the bottom concrete fiber, and then we have tension in steel as well. Neutral axis is located somewhere which is at a distance C from the top fiber, and the tensile extreme tensile fiber of concrete is located at a distance which is YT. We have compression in concrete, tension stresses in steel, and then we have tensile stresses in uh, steel as well. These are the tensile stresses in concrete. So as we know, we have a flexure formula, which is uh, actually F is equal to my over I. If we rearrange, M is equal to Fi over Y. F is the tensile strength, or in this case we have flexural strength of the concrete. Ig is the gross moment of inertia, and Yt is distance of the extreme concrete fibers in tension from the neutral axis. This Yt, this is the neutral axis, and this Yt is the maximum distance, or the distance of the extreme concrete fiber in tension. For Fr, we already have an ACI equation which we discussed in our previous lecture, which is 7.5 into under root F dash C. We can calculate this value by putting in the value of F dash C, which has been given to us, and F dash C is equal to 3000 psi. So our flexural strength is 410.8 psi. Moving forward, we already know that this is uh, um, basically a symmetric section, and its centroid is at the mid spans, at the midpoint actually. So this C and YT are actually equal. If the total depth is 30, C and T will be equal to 15 inches. So we don't need to go into further calculation. We can directly take it as 15 inches and calculate the gross moment of inertia. We are right now considering the gross moment of inertia because the concrete section has not yet cracked. We just reach the point where concrete starts to crack. So till that point, we have to consider the total cross section of the beam. After that point, we have to ignore the concrete in tension. We have to only take the concrete in compression, which is still intact, and then the area of steel, which is taking tensile stresses. So in this case, we have to take the gross moment of inertia, and you already know that moment of inertia is calculated by using this equation, which is bh cubed by 12. Uh, we have 15 is the width, 30 is the total depth divided by 12. So our gross moment of inertia is calculated as 33,750 inch raised to power 4. So for this equation, we have already calculated Fr, we have calculated gross moment of inertia, and we know that Yt is equal to 15 inches. We can put in the values in that equation, and our cracking moment comes out to be 924,300 pound inches because this Fr was in pounds per square inch. Gross moment of inertia was in the units of inch, and this Yt was having units of inch. So it comes out to be in pound inches. If you convert it into kip fit, you have to divide it by 1000 to convert this pound into kips, and then you have to divide it again by 12 to convert this inch into feet. So it comes out to be 77 kip fit. So this is the cracking moment of this section. It has nothing to do with the applied load because this is a property of the section, the moment at which the concrete in tension starts to crack. So we already have an applied load, and our second requirement is to check whether the section has cracked under the applied load. For simply supported beam, you know that the maximum moment is at the midspan, and you can easily calculate this maximum moment by using this equation, which is WL square by 8. So we have W of 2 kip per feet, L is 20 feet, which is given, and you can put in values in this equation to calculate the applied moment. So your applied moment is 100 kip feet. Your cracking moment is 77 kip feet. It means at 77 kip feet, um, cracks will be initiated, in your section, but your applied load is already 100 kip feet. So it means under the applied load, which is greater than which is causing moment which is greater than the cracking moment, it means that our section has already cracked, so it is a cracked section. So this is how you can calculate the cracking moment for a given section, and then compare the moment because of the applied load, and you can check whether your section has already cracked or it is still intact. It is an uncracked section. So in this case, it is a cracked section. Okay, then coming to a reinforcement ratio, we'll be using it quite frequently in our reinforced concrete design. Reinforcement ratio is basically the ratio of uh, area of steel to the area of concrete. So, but we take the effective area of the concrete, which the total area of concrete is actually B into H, but the area of concrete below the centroid of the steel is ignored. So we'll take it as AS over BD. This is B and this is D, which is 2.5 inches less than the total depth of the beam in this case. So we'll always use reinforcement ratio of AS over BD in the case of reinforced concrete beams. So talking of reinforced concrete reinforcement ratio in this case, the example which we already solved, we had four number 8 bars, and to calculate reinforcement ratio for this case, we have to first calculate the total area of steel, which is 4 is for total number of bars, and then pi r square is for area of steel. Number 8 bar has a diameter of 1 inch and radius of 0.5 inch, so you can put in the value of radius in this equation, multiplying it by 4 because you have total 4 number of bars. So your total area in this case is 3.16 inch square. So you have the value for width of the beam and effective depth of the beam. So you can put in all these values in this equation to calculate the actual reinforcement ratio which has been used in this section, which comes out to be 0.008, or if you multiply it by 100, it comes out to be 0.8%. So your reinforcement ratio is normally in the range of 1% in case of singly reinforced beams. Uh, so this is actually the uh, currently used reinforcement ratio, but we have some limits for these reinforcement ratios as well. We have minimum limit and then we have maximum limit for this reinforcement ratio because of different reasons. The minimum value of this reinforcement ratio is given by these two equations, which is 200 over Fy, which is the yield strength of steel used, or 3 under root F dash C over Fy. Whichever is greater, that is the minimum value for the reinforcement ratio. This is as per ACI code section 10, to be precise, section 10.5. So this is the minimum reinforcement ratio which you have to use in case of a reinforced concrete beam design. And coming to the maximum reinforcement ratio, before going to the maximum reinforcement ratio, we have to check in uh, the failure case of this beam, the point at which the beam fails under the applied load. Uh, Only then you can understand why this maximum value of reinforcement ratio has to be followed precisely. Okay, so we have the given beam which is having section as given, and now your compression strain in concrete has reached its ultimate limit. It means it will fail at this strain, which we discussed in our previous lecture, and the value for this strain is 0.003 as per ACI code. Uh, we have some strain in steel. Concrete has already cracked. There are some stresses in steel, and at failure point, we'll assume that it has reached its yielding stress. Uh, in this case, we are using Whitney's rectangular stress distribution block, which we discussed in our previous lecture, because at this point we have a parabolic distribution like this. So we convert it into rectangular distribution for ease of our calculation, and this depth of this rectangular block is actually less than the total depth of the concrete in compression, which was C, but now this depth is A, which is given by beta 1 C, and the value of beta 1 ranges from 0.65 to 0.85 for the concrete compressive strength of less than equal to 4000 psi, which is the most common case in which we'll be using. That value of beta will be given by will be equal to 0.85. But if the concrete compressive strength increases, so for every 1000 increase in compressive strength, your beta 1 reduces by 0.05. It means for 5000 psi concrete, beta 1 will be equal to zero point 0.8, and then for 6000 psi concrete, it will be 0.75, but the minimum value is 0.65. It means at 8000 psi concrete it will reach 0.65, but even for 9000, 10,000 psi or greater compressive strength concrete, you have to use value of beta 1 equal to 0.65. Okay, so for equilibrium, for force equilibrium, we have compression, total compression force in concrete, and total tensile force in steel. So we'll take it both equal for force equilibrium. So tensile force in steel is equal to compressive force in concrete. Tensile force is given by area of steel into stresses applied, so AS, Fy, and similarly in concrete it is stresses, which is 0.85 F dash C into area of concrete, which is B is the width and A is the total depth. So this is the area of concrete in compression. So okay, so ASFY is equal to, solving it, applying the value of A equal to beta 1 C. Uh, we further simplify it, dividing the whole equation by BD. On left hand side, we have AS over BD, and Fy goes there, F dash C divided by Fy. So AS over BD is equal to rho, which is the reinforcement ratio. We already discussed it. So rearranging this equation, we have a new equation, which is rho is equal to 0.85 F dash C over Fy beta 1 C over D. We call it equation 2. Okay, so now we'll put in the value of C over D to have to express this uh, reinforcement ratio in terms of strain in concrete and strain in steel. Okay, so we have the same section, we have the same strain profile. We have a strain of epsilon cu in concrete, which is the ultimate strain. We have some strain in steel, which is actually epsilon y at failure, but for now we take it as epsilon s, which is strain in steel. So epsilon, applying the similar triangle principle for this triangle and this triangle. So we have perpendicular, starting with this triangle, we have perpendicular of epsilon s, so perpendicular divided by base, which is d minus c, epsilon s divided by d minus c is equal to epsilon cu divided by c. Rearranging this, we have C over D is equal to epsilon Cu over epsilon S plus epsilon Cu. We can put in this value of C over D in this equation 2, which is this equation. Putting in the value, uh, we have this equation, which is rho is equal to 0.85 f dash c or fy beta 1 epsilon cu or over epsilon s plus epsilon cu. So from this equation you can clearly see that reinforcement ratio is inversely proportional to the strain in steel. It means if we reduce the reinforcement ratio, the strain in steel will increase. If we increase the reinforcement ratio, strain in steel will reduce. So a point at which concrete has already reached its epsilon, its ultimate compressive strain, and if this epsilon s or tensile strain in steel reaches its yielding strain when it is equal to the epsilon y, if we put in epsilon y in case of epsilon in place of epsilon s, that is called rho b or balanced reinforcement ratio. Balanced reinforcement ratio is the reinforcement ratio at which concrete in compression fails, and at the same instance steel in tension also fails. So you have um, the ultimate strain in concrete, and at the same point ultimate strain in steel and tension has already been reached. So this is called balanced failure. If we reduce the reinforcement ratio below this balanced reinforcement ratio, it means we have increased the tensile strain in steel, and steel will fail before the failure of concrete. It means we reduce the strength of steel in tension if we reduce the reinforcement ratio. And if we increase the reinforcement ratio, it means we have reduced the strains in reinforcement. It will go below epsilon y, which is the failure strain, and concrete will fail, but steel will not fail. But as per ACI code, we don't want concrete to fail before steel, because that concrete is brittle in nature. If it fails, there won't be any warning. There will be a sudden failure. But if steel failure is initiated before ultimate limit of concrete is reached, there will be a ductile failure. Cracks will be initiated in our reinforced concrete members, and the inhabitants will have warning before the failure. There will be excessive deflections, huge cracks, and inhabitant can vacate the building before its collapse. So for that purpose, we will always be using tension controlled section. It means that we will make sure that steel fails before concrete. So for that purpose, we have increased the value of strain in steel. So increasing the value of strain in steel means we have reduced the reinforcement ratio. We have reduced our total reinforcement in our section. So it is less than the balance reinforcement ratio. For a concrete compressive strength is more compared to the steel tensile strength, and now concrete will be intact at a point when steel will fail, and we will have a tension failure of our reinforced concrete member. So the maximum reinforcement ratio which we'll be using is when we use this epsilon t in case of epsilon s, and epsilon t is 0.005. If you want to calculate epsilon y for a 60 grade steel or 60 psi steel, you can easily calculate epsilon y because mm, the yielding stress is given, which is 60,000 psi. You know the modulus of elasticity of steel. You can calculate epsilon y, which comes out to be around 0.002, but you have increased it to 0.005, which is almost 2.5 times of the yielding strain of the steel. So if we use epsilon t equal to 0.005, that is the maximum reinforcement ratio uh, which we'll be using. You can calculate both the values by putting in 0.002, epsilon cu equal to 0.003. You can use compressive strength of 3000 psi, yield strength of steel equal to 60,000 psi, beta 1 equal to 0.85. You can calculate um, rho b at your own. Then you can put in the same values except this value epsilon t, which is 0.005, and you can calculate your rho max, and then just compare this rho max to rho b. Rho max will be a lot lower value compared to rho b. It means we have reduced the area of steel, we have reduced the strength of steel provided to that composite section, and now steel will fail before the failure of concrete, and we'll have ductile failure, or we'll call it tension controlled section, which is the only allowable section as per ACI code. So, dear students, with this we come to the end of our today's lecture. Summarizing